Hello, everybody. Good morning. Hope you can all hear me okay. Thank you for joining us and welcome to Raycastle's latest live webinar looking at open radio access networks. In this webinar, we'll aim to demystify the world of open radio access networks. It will provide a meaning for the acronyms associated with the technology. It will explain the need for open radio access networks, the key players, and the associated technologies. If I could ask you all to please mute your microphones just to ensure it's nice and quiet. And there will be a queue at the end of the session, so please add your questions to the chat box and Les will answer them at the end. First, before we get on to the main presentation, a brief introduction to us here at Raycastle for anyone who's new to us. We empower the global telecoms world by developing the specialist knowledge, skills and competencies organizations need to build, maintain, optimize and operate the cutting edge communication networks of today and tomorrow. We're founded in 1958 in Raycastle, the lovely castle you see there, and we're now HQ'd in the English Lake District, but we do, however, train worldwide with a preferred partner of many telecoms and high-tech industry giants and adjacent industries. You'll see a few highlights below. We've got some of the major operators on there like BT, Vodafone, EE. We do some of the larger vendors as well, such as Siemens, and also other government organizations such as regulators and things like the MOD, Ministry of Defence and things like that. We train on all the major telecoms technologies, including 5G, LTE, virtualization, security, radio access, and we also have a fairly extensive portfolio of telecoms business training programs. We train a wide range of audiences from experienced engineers to new starters and commercial grades and anyone within the industry essentially. So how do we deliver our training? We have innovative and effective and flexible learning solutions ranging from traditional instructional classroom courses and virtual live classroom, such as this one we're running today, which offer the same kind of interactive, engaging learning experience as face-to-face training. We also have a new portfolio of on-demand training courses where you can study at your own pace. And we also have larger enterprise-wide academies, which aim to kind of offer our training to everyone within the industry. If you want to explore our portfolio, please do our website, raycastle.com. So now getting on to the main event, I'll just introduce our trainer for today, which is Les Granfield. Now, Les has been a technical trainer for over 35 years. His expertise extends across a wide range of technologies, but he specializes in GSM, GSMR, ERMTS, UMTS, and LTE radio access, network planning, network optimization, and puck-to-talk over cellular. Right, that's all from me. So I'll hand over to Les, who will run you through the webinar content. Okay, Les, I'll just stop sharing my screen so you can share yours.
Okay, thank you, Paul. So good morning, good afternoon, everybody. Just bear with me for one moment while I just launch my presentation. First of all, one of the problems with a new technology is all of the acronyms and abbreviations. So I thought I'd just sort of kick off with a quick explanation. Hopefully the first one shouldn't cause too much of a problem. So the RAN is the radio access network. But over the years, we have different types of radio access networks, going back to the days of 2G, GSM. The radio access network was more correctly known as the base station system, the BSS. And then when 3G, UMTS came along, the Universal Mobile Telecommunication System, the radio access network was referred to as the UTRAN, the UMTS terrestrial radio access network. And then following on with 4G LTE, long-term evolution, the RAN was then referred to as the evolved UTRAN. And now, of course, with 5G, we have a completely new network, a completely new radio access network called the next generation RAN. So there's 4 abbreviations before we begin. However, when we start to look at ORAN, well, ORAN is a 4-letter acronym and it stands for Open Radio Access Networks, and it's a general term. And our one-day ORAN course is a general course looking at all of the various ORAN technologies. And within the course, and today, in fact, also, we will meet another abbreviation called O-RAN. Now, this is the term that's actually used by the Open RAN Alliance, which is often written down as O-RAN Alliance. And we'll take a look at what they do this morning. But there's another Open RAN to be aware of called Open RAN with a capital O. So it seems we've got an ORAN, an O-RAN, and an Open RAN. And unfortunately, those terms do get mixed together quite often, and that can lead to some confusion. Now, the radio access networks to date, just to introduce yet more abbreviations, we go back to the early 90s with GSM. The BSS, now often called the RAN, would consist of a base station controller and attached to it a large number of base transceiver stations. And the BSC will then connect back to the core network, and it's the job of the BSC to control all of the radio functionality within the radio access network. Some 10 years later, when 3G came along, we don't have a new core network. We carry on using the existing core network, but the RAN changes. We have a new radio network controller, an RNC, and new base stations, which are referred to as node Bs. And then some 10 years later, when 4G comes along, notice we lose the radio network controller. There is no base station controller. So we simply have new base stations referred to as evolved node Bs or EMBs to their friends, and they connect directly into the new core network, the evolved packet core. So the intelligence that we had in the RNC and the BSC in previous generations, that intelligence has been moved into the base stations. So these are far cleverer than their predecessors. And then the step from 4G to 5G is not remarkable insofar as we, again, still have no radio network controller. We still have our intelligent base stations. They're now referred to as next generation node Bs or GMBs to their friends. And the GMBs connect directly into a brand new 5G core network. So again, the GMBs are a lot more intelligent than, again, their predecessors, in particular the 2G and the 3G base stations. So having got the acronyms and abbreviations out of the way, why do we need open radio access networks? Well, I think mobile operators have enjoyed a considerable amount of success over the sort of the previous 30 years, but many now face or find themselves on the precipice. And the reason I say that is because I would guess about 65% of the world's population has at least one mobile subscription. And 65% of the population, the world's population, is 4.8 billion subscribers. So do you think it'd be possible to perhaps sign up the remaining 35%? Well, statistics suggest not. If we would look at subscriber growth in recent years, this particular graph shows what was happening in the year 2020. The subscriber growth was something like 4.2%, and it seems to be leveling out. And the other problem we face is traffic. Traffic is increasing almost exponentially. So between the years of 2016 and 2021, the traffic growth experienced by most mobile networks was up to about 47%. And this has largely been driven by the popular use of smartphones, for example. So basically, we need more capacity. And the capacity is not an issue in the core network. The capacity issue is in the RAN, in the radio access network. So we need more cell sites. We need more base stations. So potentially this is going to be proving to be very expensive. So it's been estimated that about 65 to 70% of the total cost of ownership is actually in the RAN. And clearly, if we need to put more capacity in, this is only going to increase. So we need a much cleverer way of putting more capacity into our radio access network. And this is where Open RAN comes in. So if we just have a quick look at the generic structure of a mobile network, we've got the radio access network shown in red at the bottom. We've got the core network in green at the top, and connecting the two, we've got a transport network. But we're just simply going to focus on the radio access network. And when you look inside a GSM network, a UMTS, 4G or 5G network, the components within the RAN will consist of both hardware and software. And traditionally, the hardware and software has been sourced from one vendor. What we need to do to create an open RAN is to perform disaggregation. And disaggregation is separating the software from the hardware. And what I mean by that is actually being able to source the software from one vendor, and the hardware is then supplied by a separate vendor. And that has never been the case previously. We always have to get the software and the hardware. It comes in one package from one vendor. So we're always locked in to one vendor. We can make more economical sense of the system if we can actually separate this hardware and the software and source them from different vendors. Now, if we look at a sort of a contemporary base station, with a contemporary base station, at the bottom of the mast, we'll have a device called a baseband unit, a BBU. And the baseband unit does all of the baseband functionality, things like channel coding, error correction, burst building, perhaps, inverse fast Fourier transform, that type of activity. And at the top of the mast, we'll have a remote radio unit, an RRU, which does modulation and demodulation, transmission and reception. And the RRU would connect to the BBU, typically using a fiber optic connection, possibly using something called CPRI, the Common Public Radio Interface. We also need to feed power up the mast as well to actually provide power for the radio unit. Now, traditionally, the BBU and the RRU have always been sourced from the same vendor. In ORAN, what we need to do, as mentioned, is perform disaggregation. So if we take a look at the BBU, what I need is a commercial off-the-shelf server, which I can source from any and many different manufacturers. I can then load into that hardware platform some proprietary software, possibly with virtualized functions as well. At the top of the mast, what I need is a general processing platform, again, a commercial off-the-shelf server. That will be my hardware. And I can then load into that hardware various software packages from, again, different vendors. And depending upon the type of software, I can create different functionality. I can create a GSM BTS or a 4G LTE base station or a 5G new radio. Okay, this is achieved by what was referred to as software-defined radios. The interface between the two, the RRU and the BBU, needs to be an open interface. And unfortunately, CPRI, the Common Public Radio Interface, which has been around for quite a few years now, isn't quite an open interface. But we have a new version called eCPRI that's been designed specifically for 5G, and that is in fact an open interface. So just have a quick look at the organizations that are involved in ORAN, and 3GPP, the Third Generation Partnership Project, have addressed this particular issue. On the left-hand side, we have the original architecture with the baseband unit at the bottom of the mast, remote radio unit at the top, the connection between the two, as mentioned, using fiber optic. That's often referred to as the front haul interface. And the connection from the BBU back into the core, whether it be a 5G core or an LTE evolved packet core, is referred to as the back haul. Now, what 3GPP have done in their technical report 38.401, they've split the BBU into two parts, a centralized unit and a distributor unit. And connecting the two together, we have another transmission system called the mid-haul. The CU connects back to the core over the back haul, and the DU connects to the front haul, I should say the remote radio unit over the front haul. So the idea is we can actually have one centralized unit looking after many, many distributed units, potentially 100 DUs attached to a centralized unit. The mid-haul is going to be a 3GPP defined open interface, referred to as the F1 interface. The front haul, however, has not been defined by 3GPP, but it's likely to be based on eCPRI, for example. Now, the reason why 3GPP have approached the architecture in this way is because we have then the flexibility to split our protocols. You may be aware that the protocol stack on the radio interface, the so-called access stratum, is made up from different layers, layer 3, 2, and 1. So the idea being the higher layer protocols, such as radio resource control, the packet data convergence protocol, could be located in the centralized unit, and they could in fact be virtualized. So the CU itself could in fact be in a cloud on a computer server somewhere accessible via the internet. The DU would support the lower layer protocols, such as radio link control and medium access control. And then the RRU would just simply support the layer 1 protocol, the physical layer. But the exact split of those protocols between those units should be highly flexible, and that gives the mobile operator the choice of rolling out a particular network configuration. Now, as well as 3GPP, another organization that's involved in ORAN is the Telecom Infra Project, TIP. Their focus is really on deployment and the execution of the ORAN. They were founded in 2016. They're divided into 3 project groups, but the project group of interest is the Access Project Group. And in green, there are 3 which are of interest in particular, one being Open RAN, and their main objective is to have a fully programmable radio access network, and the solution is going to be based upon a generic processing platform. They've also specified the Open RAN 5G new radio, which is often referred to as a white box. And this white box 5G new radio uses open and disaggregated architecture. And they're also looking at vRAN fronthaul. So instead of using perhaps CPRI or eCPRI, why not use something like Ethernet or GFAST or GPON as a means of connecting the DU from the RRU? Now, as well as TIP, a big organization that's developing standards for ORAN is the ORAN Alliance. Now, they were formed back in February of 2018 as a merger between the C-RAN Alliance and the X-RAN Forum. And when you look on their website, they quote 2 visions. Vision 1 is looking at openness, and openness is referring to open interfaces that will actually enable multi-vendor deployments. And this should then create a more competitive and vibrant supplier ecosystem. So we're going to be using open source software, hardware reference devices that will actually enable faster and permissionless creativity. Yeah, those are words taken really from the ORAN Alliance website. The automation business, well, base stations and RANs are becoming increasingly complex. So we need to simplify the operations and maintenance, which in turn will reduce operational expenditure. So the idea is to actually embed artificial intelligence into the RAN and using machine learning algorithms so that the RAN itself can monitor itself and actually self-optimize. Our Alliance are responsible for developing standards, and they've got also a framework for interoperability testing, and they do work closely with TIP. So what's been produced? Well, within the 3GPP environment, we've got what is now referred to as a split architecture. So when we look in the next generation node B, we are actually splitting the system up into the centralized unit. So we have a GMB CU, and then we have the 3GPP defined open interface, F1, connecting to our distributed units. So the GMB DUs can be supplied by one vendor, and they can be connected to the GMB centralized unit, which can be sourced by a completely different vendor. And as mentioned, what we can run in the centralized unit is RRC, PDCP in the control plane. And that could be based on the cloud, so we can actually have those functions virtualized. And then we have an open interface to the DUs, and the DUs will be executing things like radio link control, medium access control, and the physical layer. In terms of the ORAN architecture, well, looks nothing like a base station, rather a strange and a curious picture. But within the ORAN architecture, this is the high-level architecture that we're looking at here. It's all divided into three parts. At the top, we have what's referred to the Service Management and Orchestration Framework. In the middle, we have the ORAN network functions. And at the bottom, we have the O Cloud. Well, the Service Management and Orchestration Framework is providing management service for the radio network, but also for the core network and perhaps the transport network. And it also deals with network slicing as well. So it's actually there to manage and operate the RAN. The RAN itself consists of the ORAN network functions. So within here, you will find the 3GPP defined distributed unit and the 3GPP defined centralized unit, but they're referred to as the ODU and the OCU because these are specified by the ORAN Alliance. And then the O Cloud at the bottom is essentially the hardware platform. So the ORAN network functions are essentially virtualized, and those virtualized functions clearly need a real hardware platform. So the hardware is referred to as the O Cloud, and that's where you'll find the ORAN centralized unit, the ORAN distributor unit, and they'll be executing the protocols as mentioned. Now, to allow these devices to interwork with one another, there are some ORAN Alliance defined interfaces. So we have the O1 interface connecting the SMO to the ORAN network functions. The O2 interface connects the SMO to the hardware platform. And then we have another interface called the A1 interface, which connects together two strange looking things. We have at the top something called the non-real-time RAN intelligent controller. And in the ORAN network functions, a near real-time RAN intelligent controller. Now, this is clever. This is where we can introduce artificial intelligence and machine learning. So these functions will allow us to, or allow the radio access network to perform self-supervision and self-optimization. So some of the self-organizing network techniques, the SON techniques, which you may have met, such as mobility robustness and radio resource management, those types of things can be executed in these non-real-time and near real-time RICs. We also have an open frontal M-plane interface connecting to an ORAN RU. An ORAN RU can't be virtualized, so it's sort of drawn as a separate thing here. And so it needs to be managed, and that's done over the so-called open frontal M-plane interface. M for maintenance is the term here. And finally, just to finish off, you know, just have a quick look at a telecom infra project white box base station. And as we can see, we've got the traditional 3GPP defined architecture with a centralized unit connected to the distributed unit over the mid hall, and then the DU connected to the RU over the front hall. And with TIP, they've defined or decided that the front hall should be based upon eCPRI, which is ideal for a 5G base station. In fact, this is the 5G new radio base station architecture that we're looking at here. It mentions something called the 7.2x split. Well, that's something we'll go into more detail in on the actual one-day ORAN course. But the actual base station itself is designed to support 8-layer downlink MIMO with 4-layer uplink MIMO. It supports beamforming. In the RU itself, we actually have essentially field programmable gate arrays, application-specific integrated circuits, which are executing the lower layer fast Fourier transform, inverse fast Fourier transform, and supporting the physical random access procedure. We've got a digital front end performing digital processing and a radio frequency front end, which includes bandpass filters, low noise amplifiers, power amplifiers, and such like. And then there's a collection of other peripherals shown on the right-hand side, such as the actual power supplies, LED indicators, a GPS receiver for TD operation perhaps. And to provide the frontal connection back to the DU, we need some kind of a transport network interface card. Within the DU, again, field programmable gate arrays, supporting, sort of supported by central processing unit cores, executing the so-called physical high, RLC and MAC functionality, whereas the RU performed the lower physical layer functionality. And again, we need transport connectivity back to the centralized unit for the mid-haul. And within the centralized unit will be the x86 processing platforms or ARM processors, and we can virtualize the higher layer protocols, such as the packet data convergence protocol, the SDAP protocol supporting traffic, and the layer 3 protocol RLC supporting signaling, and then backhaul connectivity back to the core network over the NG reference point. A very, very brief overview of ORAN. We'll go into a lot more detail on the one-day course, but for now.
Thanks, Les. A really interesting overview of ORAN. And thanks everyone for attending. If you'd like information on our one-day training course, you can see details here. If you'd like to register and book, please go to our website, raycastle.com. Thanks, and see you next time.